Hello everyone, I'm Qiliang coming from the Hong Kong Polytechnic University. I'm very glad to be here to share my latest research. My topic today is negative thermal flux phenomenon and regional solar coating optimization for next generation solar power tower. I will introduce my work from five aspects. First is the development of the solar power tower. As we all know, concentrating solar thermal power is one of the solar power generation technologies because CSP has the advantage of the thermal energy storage. It has aroused considerable interest from the researchers worldwide over the past 10 years. We can observe from the list two pictures that global CSP capacity in operation grew exclusively in the last decade, particularly in emerging markets. Besides, the thermal energy storage capacity also increased rapidly in conjunction with the CSP plant. Therefore, as an important technology, though the CSP capacity is still small, but learning and developing very fast. To date, the concentrating solar thermal technology mainly includes parabolic trough collector, Fresnel collector, tower collector, and parabolic dish collector. Among them, the tower collector is widely regarded as the most promising technology used in the future due to its high operating temperature. The solar power tower system was mainly composed of solar receiver, heat exchange, power block, and thermal energy storage. The tower receiver is responsible for the solar energy absorption and conversion, so it is thereby the key component of the SPD system. For the tower receiver, it has two important features. The first is the uneven solar flux distribution on the receiver surface. A minimum concentrating ratio is only 10 at edge regions, but the maximum concentrating ratio reaches about above 1000 at center regions. The second is its high temperature. The heat transfer fluid used in commercial SPD system is generally solar salt, which can reach 560 degrees. For the next generation SPT, novel thermal carriers such as supercritical carbon dioxide or other molten salt will be used to achieve much higher temperature. To absorb solar energy as much as possible, the receiver surface was covered with one single coating. The coating in the current tower receiver is usually pyromac paint. It has high solar absorbance, about 1.94, and high thermal emittance around 1.88. For the next generation SPD system, higher temperature and high thermal emittance of the coating will cause higher heat loss, mainly radiation heat loss. As mentioned just now, the edge regions of the receiver surface has low solar flux. Considering high heat loss and low solar flux at edge regions, we thereby proposed a hypothesis that is whether the heat loss at edge regions is higher than the absorbed solar flux. If so, that means the negative heat gain of tower receiver will exist at edge regions. In this context, how to reduce the radiation heat loss and thus improve the thermal efficiency for the next generation SPT. If the negative heat gain exists, then we will introduce the regional coating optimization method to solve this this problem. In this study, we selected the Dunhuang 10 mW SPT plant, and the study case, its layout and heliostat distribution are shown in the left two pictures. The three-dimensional view and air view of the tower receiver are shown in the right pictures. The heat transfer fluid used in this next generation tower receiver is magnesium-based molten salt, and its stability point can reach above 800 degrees, and the whole receiver is divided into two flow paths. From the northern to southern side, the inlet and outlet temperatures are set at 420 and 760 degrees respectively. In above context, we also established a heat transfer model for computing the thermal performance of tower receiver, as shown in the left picture. The three-dimensional cylindrical surface of tower receiver spread out into two-dimensional plate, and the plate was further divided into 468 rectangular regions for the detailed thermal performance of each position in the tower receiver. The related calculation equations are presented here, but due to the limited presentation time, we will not explain the equation here anymore. In order to verify the mathematical model, we used the experimental data of Solar 2 power plant to compare with the simulation result. As shown in the table, we can see that the relative error maintained within 2%, and the root mean square deviation is only around 1.7%. This demonstrates good prediction ability of the mathematical model for the thermal performance of SPT system. Based on the above mathematical model, we calculated the annual average solar flux distribution on the receiver surface, as shown in the picture. We can see that the distribution is highly non-uniform. High concentrating ratio reach around 1,500 and central regions, but only 7 to 10 concentrating ratio occurs at edge regions. Subsequently, we also calculated the annual average receiver temperature distribution on the receiver surface. We can see that for the next generation SPT system, the average receiver temperature of the whole receiver surface reached 740 degrees. Accordingly, the radiation heat loss distribution on the receiver surface was calculated. We can see that the radiation heat loss distribution is similar to the receiver temperature, and the average radiation heat loss is extremely high and becomes the major factor resulting in the massive heat loss of whole tower receiver. Based on the obtained solar flux and heat loss distributions, we calculated out the net heat gain of each region in the receiver. Just as we expected, a negative heat gain phenomenon occurs at edge regions close to southern side. We call these regions the negative thermal flux region, that is NTRs. It is calculated that the number of the NTR reaches 111, almost a quarter of the entire receiver, which seriously affecting the thermal performance of the tower receiver. In this context, we are thinking about how to take full advantage of the NTR to enhance the receiver efficiency. In this context, we proposed the regional coating optimization method. We changed the original black pyromark paint into other coatings with lower emittance. In this study, we selected silver-based coating and black chrome-based coating for study. We can see that the table that the emittances of the silver-based coating and black chrome-based coating are only 0.06 and 0.4. But the solar absorbance are reduced to 0.2 and 0.9. Then we calculated the thermal performance of the novel receivers with silver-based coating and black chrome-based coating. The net heat gain maps of these two kinds of novel receivers are presented here. We can see that the number of the regions with negative heat gain is reduced to 84 and 64 in the novel receiver 1 and 2 compared with prototype receiver. Correspondingly, the radiation heat loss in NTRs are significantly reduced by 93 and 53% because of the very low thermal emittance of the silver-based coating and the black chrome-based coating. But due to the reduced solar absorbance, the amount of the solar absorption by NTR decreased by around 78 and 4.5%. But overall, the net heat gain in the NTR for the novel receiver 1 and 2 are effectively enhanced to minus 0.2 and minus 0.4 million watts from the original minus 2.5. As a result, the receiver efficiency of novel receiver 1 and 2 are effectively enhanced by around 6.5 and 6%, demonstrating that the coating optimization method exerts effective role in enhancing the thermal efficiency of tower. The thermal performance of the novel receiver under different direct normal irradiance on the none of the thermal sources is also investigated. It can be seen that two kinds of novel receiver achieved superior thermal performance at the DNI from the 500 to 900 watts per meter square, and the largest increase of the heat gain of the novel receiver is achieved at lower DNI of 500 watts per meter square, where the receiver efficiencies are enhanced by 11 and 9% compared with the prototype receiver. Besides, the novel receiver 1 possesses the best performance at low DNIs below 550 watts per meter square, and the novel receiver 2 has a higher efficiency above at high DNIs above 750 watts per meter square. In addition, the thermal performance of the novel receivers under different solar hours on the summer solstice is studied. The detailed DNIs and different solar hours are presented in the table. By the calculation based on the mathematical model, the receiver efficiency of three kinds of the receivers are shown in the pictures. We can see that both novel receivers maintain superior thermal performance throughout the day, particularly in the morning and the evening. The last part is the conclusions. The first is the mismatch between the solar flux and the radiation heat loss distribution leads to a negative thermal flux phenomenon at each regions of the tower receiver close to southern side, and the Nova receiver 1 with silver-based coating, and the receiver 2 with black trim-based coating obtained great successes in enhancing the receiver efficiency, the annual average heat gains, and receiver efficiencies of the Nova receiver 1 and 2 thereby have breakthrough enhancements by around 6.5 and 6% compared with the prototype receiver. The Nova receiver 1 possesses the best performance and lower DNIs below 750 watts per meter square, while the Nova receiver 2 surpasses the Nova receiver 1 and the best performance one with DNI exceeding 750 watts per meter square. Both Nova receiver 1 and 2 maintain superior thermal performance at the morning and the evening. That's all for my presentation. Thanks for your attention. Thanks for the sponsorships by the RGC postdoctoral fellowship scheme and postdoctoral help program. Thank you.